Welcome everyone to this week's Nordita seminar. Today we have Anshuman Acharya. He's a PhD student at the Max Planck Institute for Astrophysics in Washington. And before this, he did his bachelor's and master's in Aizawl Mohali in India. Yep. He mostly works within the LOFAR Epoch of Reionization working group, working on both developing theoretical models for LOFAR and also trying to improve the data analysis pipeline for LOFAR. And today he'll talk about one of his work in developing the data analysis pipeline.
Okay, so hello everyone. As introduced, I'm Anshuman. I'll be talking about detecting the epoch of reionization 21 signal, machine learning upgrade to GPR, which is a lot of words. So before going into that, I'd like to thank my collaborators, including my supervisor, Benedetta Acharya. She's been absolutely wonderful for supporting me in this project. And of course, Sambit for inviting me here. So let's start. So the very first thing that we need to know from all of these words is the epoch of reionization. So I'll try to go to introduce each and every word of this title before we go into what we are, what I'm actually doing in this. So to give a quick recap, what we say as the epoch of reionization refers to this period, which is when after the first clouds of neutral hydrogen form, which is when the protons and electrons were finally reaching to a state where they had enough loss of energy that they can now combine together to form the first atoms, which was mostly hydrogen, a little bit of helium. And that led to the dark ages, where there was just clouds of hydrogen everywhere in the universe, and nothing much happened. Like there was no sources of photons. But the first sources did start appearing from the period which we call cosmic dawn, and that starts the period of the epoch of reionization. So this is the period when we have the first stars, and which eventually would also mean that this is also the period when we have the first galaxies forming, the first black holes, or whatever, like any astronomical object that you would find of interest formed during this period for the first time. And what they led to was that all the neutral hydrogen that was there before, apart from the amounts that went into forming them, was slowly getting injected with photons from these objects, all these astronomical objects. These would then lead to regions like, as you can see here, there are almost a sort of bubbles shown in this representation, where the region around this astronomical object would be ionized hydrogen, and beyond that would be neutral hydrogen. So to understand how we went from the dark ages to present day, where most of the neutral hydrogen is ionized, we need to look at the epoch of reionization. And what it tells us about the universe is pretty much everything. It tells us about how did the first stars, galaxies, and everything form? What was the rate of formation? How fast did they evolve over the course of this period? And how did that affect the distribution of these objects throughout the universe? So there's a lot of questions of astrophysics that can be answered by looking at this period. So that's great. So how do you actually study the epoch of reionization? Well, there are a lot of different ways. For example, right now, the JWST is trying to look further back into the early universe to look at the first galaxies that were formed, which would be around this period. That's a great way. Another way that we are interested in as a part of the LOFAR collaboration is to look at the 21 centimeter line of neutral hydrogen. And that brings us to the next part of the title, which is the 21 centimeter signal. Again, I'll just go through it quickly so that we are all on the same page. Yeah, so the 21 centimeter signal is from neutral hydrogen, and neutral hydrogen consists of a proton and an electron. Both of these have a magnetic dipole moment associated with their spin. So in this figure, which is quite popular among people working in reionization, we have two types of hydrogen atoms that can exist. One, where the dipole moments are aligned. So we call that as the parallel case. And the other, where they are opposing each other, and that's the anti-parallel case. So the magnetic fields generated from these dipole moments would be adding up in this representation and canceling out to a certain extent in this representation. So what this canceling out means is that the overall energy of the atom would be reduced. And as we know, everything in the universe wants to be at the lowest energy state possible. So ideally, when one would look at this, we can argue that there's a tendency for atoms like this to go to atoms like this. And that's what we propose. And we say that if a photon of certain amount of energy is released, which corresponds to a wavelength of 21 centimeters, then this change can happen. But there's a catch. This difference, like this photon, the amount of energy that it carries is really low. It's of the order of like micro electron volts. So what this means is that this change is negligible. And in general, what is suggested is that this is called a forbidden transition, which basically, if you simplify the calculations, like the Einstein coefficient being very low and the half-life period of this being very high, it basically boils down that we assume that if you have hydrogen atoms, in general, you would not see them releasing a photon in order to reduce their energy. They would just be colliding with each other, and that would be enough to de-excite them for going from this state to this state, which is, again, fairly reasonable. Then how exactly would we get a signal? We are usually looking for photons, and if you are saying that photons are most likely not going to be produced, then how exactly does it happen? Well, there are, again, a few things that come into play, which give us an advantage. The first is basically the density of hydrogen clouds. If you have really low densities, like, for example, just one atom per cubic meter, what this would essentially mean is that now you have atoms which are so far apart that they would not be colliding with each other so frequently anymore. So now you have created the condition for one atom to have the possibility that it emits energy radiatively. And that's great. Now you have one atom which gave you one photon. But that's, again, you would say that how would we observe something which is just giving you one photon per atom? Well, there's another catch which the universe bestows upon us, and that is that there's a lot of hydrogen in the universe. What that means together is that you have low densities and lots of hydrogen, which gives you the possibility of detecting 21 centimeter photons. But that's the key word, detecting, which was, again, a part of the title slide that I'd shown you. And that's what we'll look into next. And this is where things start getting a bit more interesting, a bit more difficult. But again, that's why we are doing the science. So here is a pretty busy plot. I'll explain it one by one. So on the x-axis, we show the redshift. And on the y-axis, it's an interpretation of the power spectra, which basically tells you how strong is the 21 centimeter signal at a particular redshift. Then what we do is we generated two simulations of the 21 centimeter signal, one given with the dashed line here and one which is the dotted line. You can see that they are very different, but that was the idea. We wanted to create two simulations which were as far apart in terms of properties and try to see how does it look like when we represent it on this plot. And then what we show here are these red lines, which are basically the theoretical best case limits for a particular telescope, here LOFAR, and a particular observation time. This is 1,000 hours. And that's similarly, we have shown it for a few other telescopes. NENUFAR and SK are like planned observations in the future. Lastly, we have a bunch of points. And these points are basically upper limit observations that have been performed using different telescopes. What you can see immediately is that the points are spread till about 10 cube, and the highest that you are getting with the simulations is definitely lower than that. For example, if you compare the highest point of this simulation, that's something to the power 10 square, while the best point, which is right above it, is at about 10 power 4. So that means that even right now, like what we are having is something which is almost 2 orders of magnitude off. So we have upper limits, but we are still not reaching the actual signal. We are just able to say, okay, if we have the 21st century signal being there somewhere in our data, it's definitely less powerful than whatever this value is. And that's basically what all of these points say for each redshift. And this is mainly because we are dealing with data where we have massive amounts of 2 things, the foregrounds and noise. So what exactly does that mean? Well, foregrounds is quite a lot of things. We can start with remembering that we are looking at a period which is of redshift, say 6 to 15. The exact limits would be somewhere like they are always constantly being changed. But let's say that this is the period where we are most interested to look into. And that's really early in the universe. It represents this area in this demonstration. And you can see this says years after the Big Bang. That's just 1 billion years after the Big Bang. So that means that from 13.8 billion years, you're looking back to a period which is almost 13 billion years in the past. And that's really early. And the way you look back is basically you look further away. The problem with this approach is that now you have a lot of things that are going to be in the way. One of the most notable sources of things that are in the way is, of course, the Milky Way. What happens here is that you have basically a lot of local stars and different objects, astronomical objects, which are blocking your view. You have to remove all of them. And once you're done with removing all of the objects from the Milky Way, you have another problem. There are many more galaxies and stars and everything else beyond the Milky Way as well. And each of them, like if you're taking this image in the radio, all of these are there and more. And you have to subtract all of this before you reach till the redshifts where the 21st century signal is of the reionization era. So that means that you have data where more than 90% of all the photons you're getting are foregrounds, and you need to remove all of that. And the next issue is noise. Noise is still fairly understandable. Any experiment that we do would involve noise. What that means is that you would have noise from like random errors, or there can be noise from systematics, from your instruments used. And there's also noise because we are our radio telescopes are on Earth. So we have the ionosphere, which also emits photons and basically messes up the signal that we are receiving back on Earth. And what it means is, I guess the one that can...
They can come.
Yeah. Okay. Yeah. So what this means is that we have to deal with both of them. And the first issue of noise can be dealt with in quite simple ways. One of them is to just observe for longer. You just point your telescope at the sky for a longer duration, you would eventually collect enough photons that even after removing noise, foregrounds, and everything, you would be left with a reasonable amount that you can do your science with. And that's what we were proposing with LOFAR, that instead of looking at, say, for example, for 100 hours, we look at it for 1,000 hours. Let's see what happens. And that's actually something that they're doing. The other suggestion is obviously to have better telescopes, which is always going to be the push. And right now, even more, because we are gearing up for SKA. And that would mean that we have more stations doing interferometry, which would greatly improve the signal to noise ratio that we have and ensure that we can possibly make a detection. But all of these, or also both, like if we just increase the number of hours we are observing and also use better telescopes, and that's great. But all of this hinges on the assumption that even after removing noise, we have a good idea about what the foreground is, and we still have to remove it. So there are two options for foreground. One is called foreground avoidance, where what we do is that we look at the frequencies of photons, essentially, where there are, we believe that it's mostly a contribution of foregrounds, and we cancel them out. Like we just ignore those frequency ranges entirely. That's something that has been done with HERA, which is corresponding to these two dark blue points here. And the other is to basically try to not lose so much data. We would not remove frequencies entirely, but what we would try to do is look at those frequencies and identify which of the photons are basically from the foreground and remove them, so that the remaining photons that remain after removal of the foregrounds are the signal and of course noise, which will also have to be removed. This is what we do with LOFAR, and this red point here is one of the LOFAR points, and we have to now understand how exactly we do this, and that brings us to the next part of the title slide, and that's GPR. So LOFAR, which has a really pretty picture of the LOFAR telescope here, uses Gaussian process regression for basically identifying these different parts of a signal and then be able to distinguish between them. So we can quickly go through what is Gaussian process regression. Well, so if you have basically a data set Y, this is fairly generic. In our case, this data set is radio data, which is dependent on some function of X plus some random noise, where X would be your frequencies. Then what Gaussian process regression suggests that you could, instead of having just one function, have a family of functions, which is a Gaussian distribution. So what you can do from that is that you have a Gaussian distribution of functions which from which you can sample from and pick the one which best suits your data. So this Gaussian distribution, like even for one variable, it also depends on the mean and the standard deviation or the variance. And for multiple values of X, this would depend on the average, all of the averages of the X and the covariance between all of the values of X. So covariance gives you a matrix, which is something like this, which is basically showing how does each entry behave with respect to all of the other entries of X here. So what we can do is, well, firstly, we can represent our data in terms of this, where we have a function for the foregrounds, a function for excess noise, which is basically some systematic noise that remains after we have removed random noise. Of course, a function for our signal itself, and then, yes, the random noise. Now what we do is we try to basically look for a function using which we populate the covariance matrix, like how should it look like, and that is done for each of these to get each of these functions here. So the function that you use to populate the covariance matrix is important for us. The problem that was identified recently was that if the function that you choose, which will give you a covariance matrix or a covariance kernel, is misestimated. So think of it this way. You have a fitting function. You want to fit it to the data, but your data is doing something else. You're trying to fit it a function which is not correlating with what the data is suggesting. Then what would happen is that you would basically end up fitting to, say, noise. And then you would derive some astrophysical parameters from that, and that would be really off. Like it would not really represent what is actually there because you didn't really identify the 21 center signal. So we were like, this is something that was obviously of concern for the LOFAR team, and the idea was to try to address it. So this was where finally my project comes in, and that is to have a machine learning approach to solving this issue. So what was proposed was to use, like, instead of having just a function through which you are making the covariance kernel, what we would do is that we would use machine learning to generate the kernel. And for this, we use a large range of simulations which are generated from Grizzly, which is basically an n-body plus radiative transfer code. So what's Grizzly and why exactly are we using it? Well, in reionization physics, what people do is that they use a range of different kinds of simulations. There are some simulations like semi-numerical codes, like conventional fast. So their entire objective is that while you do not have something which can give you a timeline of events happening, you can get, like, for a particular redshift, for some particular properties, you can get a really fast running code, which gives you approximate results, which are pretty good, especially for if you are looking at something at the large scale. So you can create really large boxes of simulations and run them quite quickly and get the properties out of it for a particular redshift, and that's great. But there are also other kinds of simulations which are on the opposite side, which are 3D hydrodynamic simulations with 3D radiative transfer, like Thiessen, which are slow and very expensive. So running large boxes is a problem there. But what they do is that they give you a time evolution of physical interactions between individual particles and how does that correspond to the formation of structure and everything. So you are basically feeding in each physical interaction into it and seeing how does it evolve. So that seems like a more physical approach, but the catch is that because of the limitations, you will again end up making approximations that can hurt the kind of inferences that you draw. So both of them have certain limitations, and Grizzly is something that is in between. It's an n-body simulation that post-processes itself with radiative transfer. And what it ends up being is that it's faster than these hydrodynamic simulations and slightly more physical, because it gives you a time evolution of events to a certain extent as compared to semi-numerical codes, and it gives you reasonably good results. Like, by good here, what we mean is that it seems to match with what our expectations are for certain input physical parameters. So this is why we use Grizzly as our training set. But of course, there are certain things to keep in mind. Firstly, the method that we use, right now we are using something called a variational autoencoder algorithm. And like right now it seems pretty good because we have the benefit that once we recover the signal, we are directly comparing it with what are the physical parameters in Grizzly necessary to get that kind of signal, and everything seems great. But there is some caution to be applied, and that is that there can be biases involved. And that's where a major chunk of this project comes in. And that is to identify how well is this algorithm performing without forming any false flags or having something that is basically not working physically. So a quick run through about variational autoencoders, and before that, just autoencoders. So what an autoencoder does is that if you have a large amount of data, here it's just up to 6 values, but it can be any large number. Then if this data is expressed in terms of a certain number of parameters, here there are 4, A1 to A4, then what you can do is that you can say that, okay, I don't want to use 4 parameters, I want to use 2 parameters. I will try to reduce this parameter list into 2 parameters. And doing so is known as the encoding aspect. And the decoding aspect basically tries to do the reverse. It takes these 2 parameters, and if you have multiple data sets, you'll have a range of different values for these 2 parameters. And then you can pick any of those and then try to recreate your actual data set. So this is a decoder part. So what it helps you do is that you can basically save the amount of data that you're storing to be able to appropriately recreate the data whenever necessary. And that can also be used to identify how close you can reach to unknown data sets. What variation autoencoder does on top of this is that instead of taking point parameters like 1, 2, 3, 4, it takes a smear of like a range of distributions around this. So instead of taking a value A1, it takes A1 plus minus 2 sigma, for example, where the sigma can be basically adjusted according to your needs. And for each of those parameters, it does that. And then it samples from that to save the value of this reduced parameters called the latent state. And what this means is that basically with a limited number of training sets, what you would get is that instead of just having, say, for example, if you have 4,000 data sets, you save 4,000 sets of parameters. An autoencoder would be having only that much information to be saved. But a variational autoencoder has 4,000 distributions, from which if you sample enough times, you would be able to get a large number of latent state distributions, much more than what you had as the input data set. So you end up basically interpolating between these data sets, because instead of say, for example, saving A1, it also saves A1 plus minus 0.2 sigma, and that would correspond to a different kind of data set. And then it would have much more to learn from even the same training data set as compared to autoencoders. But there's also, obviously, there's always a catch involved. And that is that, like I mentioned, the upside is that you can recover unknown values, even like as long as they can be sampled from distributions. But the downside is that this process becomes a bit more error prone. This is because, like, to explain simply, instead of learning one value, it is learning that there's one value here given a distribution. So instead of picking just one value, it is picking a smear of values in this range. So if I ask the variational autoencoder to give me back this one value, it can do it. It will eventually do it. But it will first pick a large range of values from the distribution until it reaches this value. So when it finally reports you the answer, it will report you this value with the error of not being able to pick that value at the beginning. This seems a bit problematic. But the good thing is that for doing Gaussian process regression, once we have generated these, we have learned this latent state distribution range, we don't have to worry about the encoding error anymore. What we do with Gaussian process regression is that we use this as our to generate a covariance matrix, and to find the exact values we perform. We basically try to see, based on our data, what are the values we need to pick, and just decode it to get what we are getting. We are not really feeding in the signal. We are trying to extract the signal from our data. The signal is already there. So the encoder error part of it doesn't really matter too much to us, even though it can be of concern if you are, for example, trying to feed in a signal and then trying to recover the exact same signal again, which is not our case. So we are happy so far. So the last part of the talk, which is, do we actually get an upgrade? We have used GPR in the past. What does machine learning give to us? And that's where there are some interesting results. And we have given the following list of things to do to test this machine learning based GPR. The first thing is to try it with the most simplest case of signals. By uniform TS, I mean the uniform spin temperature, where the spin temperature is basically a way to measure how much of the 20 signal strength exists in a particular region. So if you say that the spin temperature is much larger than the CMB temperature at always, then wherever you have neutral hydrogen, it would be identifying it as regions where the amount of 20 centimeter signal generated is much more in contribution than the CMB energy in that regime. So that is a fairly good approximation based on what we understand, but it is also a simplification of our case. The other case is that the spin temperature can vary in terms of amounts. So sometimes it can also be that it is comparable in terms of its value as compared to the CMB temperature, or maybe even less. So that is basically the idea of it. Okay, not maybe less, but at least comparable in its value. So that's great. We would have two kinds of mock signals from Grizzly. But of course, just testing with Grizzly when we have also trained with Grizzly would not be a good idea. So the next idea is to test it with signals generated with other simulations. And lastly, we want to look at how well does it perform when we apply it to real data, especially real data which has been tested with older methods. So going to the first case, we have the uniform spin temperature signal, and we look at around redshift 9. And we take two cases of the noise. One is corresponding to about 10 nights of observations with LOFAR, and the other is corresponding to about 100 nights of observations with LOFAR. So I'll explain the graph here. So what we are trying to show here is basically the power spectrum of the different components of the signal versus K, where K on the x-axis is basically the wave number, which gives you an idea of the scale we are looking at. A low value of K means we are looking at the largest scales possible, and a high value of K looks at the smallest scales possible in terms of the size of the region that you're looking at. And what this means is that if you have a higher power, like for example, in this plot, we have something of about 10⁻⁶, some value into 10⁻⁶, then that means is that is the strength of the amount of variability at that particular K value, at that particular scale of the universe. So you are looking at, say, for example, several hundred megaparsec across. There's a lot of variability in this is basically contributed from the foregrounds, and that's the K why it's pretty high. Apart from the foregrounds, which is given in blue, we also have the noise, which is in yellow, the excess noise in green, and the actual 20 center signal in red. We also show this dotted line, which is basically the 1 sigma variance on the random noise in yellow, because we don't just want to cross the noise. We want to cross basically even the 1 sigma error on the noise, so that you are sure that whatever crosses this would be your signal. In the 10 nights of observations case, we see that it's not really crossing it, so which is evidenced in the SNR, and we do not have much high expectations of detection here. For 100 nights of case, we see that, okay, there are regions where it's crossing it, so maybe we have a better chance here. So let's look at the results of using the variational autoencoder based kernel versus what was used in the past. And this gives us the plots. So here the red line is our input 21 centimeter signal. The black is the one recovered with the variational autoencoder kernel. And the green and the purple dashed lines are basically what was used in the past with GPR. So we compare the black with the green and the purple and see how close are they matching with red in the 10 nights case and the 100 nights case. So there are a few key points which are immediately evident. One is that the black line is always overestimating as compared to the red line, especially for example, in the 10 nights case, that's a lot of overestimation. But at the same time, it is always in the 2 sigma error bar, which is showed by the shaded region here. And that means that even in the 10 nights case, where the other kernels were not able to have it included in their 2 sigma range, the VAE kernel was able to include the signal in it. So, and also the shape and the slope of the signal seems to be better recreated by the VAE kernel. So overall, none of them actually give you a definitive detection, but at least the VAE kernel does the best possible job here. So that's great, but we are still not detecting it. You would want to see what happens in a case where you have a chance to detect. And that is the variable spin temperature signal case, where because now this is variable, as I said, that what the power spectrum is basically telling you is the amount of variability at each scale. The variability of the spin temperature adds to it. And that means that now you have a signal which is much stronger than before, which is evidenced by the SNR, which is the average SNR is about 5 in the 10 nights case. It was less, almost 0.01 for the uniform case. And in 100 nights, it's almost 50, which is excellent. So what we expect from such a high SNR is that no matter what covariance kernel you take, we should be able to detect it. Because now The machine learning was supposed to be an improvement, but if they were using the other kernels before, they should still be able to perform when you have such a good enough SNR. So let's look at the results. Well, the results were interesting. We get, again, the key factors remain that the black line always seems to overestimate, especially in the 10 nights case. But at the same time, it's also including the signal in its 2 sigma ranges, and the shape and slope look great. But there's something interesting happening over here. What we see is that while the VAE kernel is pretty much matching the input signal, the other kernels which were used in the past are really not matching it. While they may barely be encompassing the signal in the lower k values, especially for the green one, the exponential kernel, the overall behavior seems very different. And that kind of is interesting. Like, even after having such a high SNR, why are they not able to detect the signal? And that brings back the criticism that was proposed earlier, and that was that if you have small issues, even in estimating the kernel, they can have massive differences. And this is what this plot is trying to show you. And it also shows that, surprisingly, our machine learning based kernel does not suffer from such a limitation. And that's great news. But you would, again, remind me that we need to test for biases. We are testing signals which are generated using Grizzly. What if this difference between the different kinds of kernel disappear if you look at a signal which is from a different simulation? That's what we did. Now we looked at signals from a hydrodynamical 3D radiative transfer simulation, which was from our research group at MPA. Again, they used, the sources are listed below, but anyway, they had run these simulations at about redshift 9.18, which is fairly similar and serves our purpose. So we again have 2 cases, one of the 10 nights of observation and one of 100 nights of observation. And what we see here is already something interesting in the SNR, that the average SNR is definitely higher than the uniform case, but also not as high as the variable spin temperature case of Grizzly. Grizzly had an SNR of about 5, the average SNR of about 5 and about 50 in these 2 cases, while this has 2 and 20, which is okay, it's not too much of a difference, but especially for the 100 nights case, there is a decent amount of difference. So now we want to see what kind of results we get with this. And this is what we get. Again, the black is the VAE kernel, the other 2 are the previously used kernels. And we see that, especially in the 100 nights case, we are, again, the VAE kernel has excellent recovery. Of course, the 2 sigma errors are still pretty broad. You can say that it goes from about 10 cube to about 10 over 1. So there are 2 orders of magnitude in spread, but they are still much lesser than the other 2 kernels, which are underestimating the signal and pretty much missing it in this case as well. So what this means is that there was something wrong with the kernels that were used before. And by looking into why this was the case, we found a pretty straightforward reason, and that was that they were first derived with the assumption of uniform spin temperature. That's why in that case, they worked decently enough. And given that the signal was so low, it was very difficult for us to know what is good or bad in terms of recovery, because everything seemed to be performing poorly. But once you start complicating things a bit further, changing a few things, you see that they don't perform well. And at the same time, the kernel that we have derived using machine learning seems to do well. So that kind of brings us to basically that we have tested our things. We have tested it with all these 3 cases. What remains is application to real data. And this is something that I would have to leave for future work, because at the moment we are still processing the data to clean it so that we are sure that what we are using can be reasonably applied, like we can directly apply a GPR on it right now. So to summarize these aspects, and I think I have a bit more time so I can go to another some extra slides. At the moment, what I've shown is that we will soon apply to real data and maybe even newly collected real data. And we also want to generalize our ML-GPR algorithm for SKA, which is something that we're already taking into account. And the current summary is that the ML-based kernel that we get is much better at recovery, at least in terms of the ranges we have explored, as compared to previously used kernels. And in most cases, we are able to recover the signal within 2 sigma limits. And this is, again, dependent that we have explored an SNR range which limits to about 0.01. Going lower than that could obviously affect the recoverability of your signal, which is, again, understandable. So before going for questions, I can quickly go through something more that we found interesting. And that was the case of redshift dependence. Everything that I showed you was for redshift 9, like around redshift 9. So what we thought was, what if we have other cases? We have redshift 8, redshift 10, and those will have different distributions of neutral hydrogen. You would have cases like redshift 10 is basically where there is more amount of neutral hydrogen. So it is more homogenized, like you have less number of bubbles around of ionized regions in whatever observations you take. So the signal would be weaker because the power spectrum is basically trying to look at the amount of variability. And if you're homogenizing the whatever you're looking at, the variability reduces. And that is shown by the trend of the graphs. Like the green is redshift 8, red is redshift 9, and blue is redshift 10. And this is the variable spin temperature case. This is the uniform spin temperature case. Yeah, I should have labeled these as well according to that. What we wanted to see was that if we develop kernels, which we did for each redshift, if we look at we develop a machine learning kernel for redshift 9, redshift 8, redshift 10, does that kind of get basically fed into it, and does that create a bias? Essentially the argument is that do we have a bias based on what is the redshift at which we have performed the training? So to look into that, we looked at 2 parameters, which one we called, again, for the lack of a better word, bias. And that was basically defined as the ratio of the power spectrum of the recovered value versus the input, whatever mock signal we had input. These are the input signals, and you get a recovery on top of it, like the black lines I showed earlier, and then you take a ratio of those. Apart from that, we also took the ratio of the uncertainty, because if you have a signal which is has strength of this much, the uncertainty values, if you take the raw values, would obviously be higher than a signal which is of this power. So we scaled it with the input signal to basically show everything at an equal footing. And then we compared the cases of the 3 redshifts. What we see is that for the uniform spin temperature signal case, which is the middle plot, we see that the bias is higher with increase in redshift. So at the lowest redshift, that is redshift 8, it is the lowest, which is corresponding to basically the strength of the signal. The higher the signal strength is, because the green is the highest, the more possible it is for it to be recovered. And that's why the recovered is more closely following the input signal. The spread of the uncertainty also matches this, which means that what we are getting is basically a recovery based on the actual input signal. The kernel that was used does not affect this output. This outcome is very much independent of the kernel that we've used. But we see something, again, a bit interesting with the variable spin temperature case, and that is that we get for redshift 9 is the one which has the best estimate of the bias, followed by redshift 8. What we assume could cause this issue, which we looked into, and I should have attached a plot for this, was that what incidentally happens at these higher redshifts is that for redshift 8, the excess noise, the systematic noise that we were estimating, the power spectrum of that pretty much matches it in terms of power as well as slope across all k values. So what was happening at redshift 8 and also to a certain extent for redshift 10 was because the excess noise curve goes something like this here, was that we were the kernel that we were using was not able to identify which of the values were basically coming from the excess noise and which values were coming from our signal. Because the input value of the redshift 9 signal was somewhere in between these two, it seemed to have managed to do well to a certain extent, except for lower k values. But other than that, there was not much of a difference. So this leads to this tiny region in k values where the red curve is closer to zero bias than the green curve, but the scaled uncertainty continues to show us the same picture as before. So apart from this caveat, it seems that training of our kernels was independent of the redshift that we used. That is, again, a fairly good result. And I guess now we can go for questions.
Someone for this interesting talk. Any questions? Also look at Zoom. I have one question. So in the redshift dependence plot, you commented that the ability to recover the signal depends on the strength of the true signal, and that thought led me to think about your plot where you show the recovery for uniform spin temperature and variable spin temperature, and your uniform variable spin temperature 21 centimeter signal had the highest strength than the uniform one. So how much do you think it's driven by the strength and the variability of TES?
Yeah, so it is pretty much like, because once you have higher if you have a higher signal to noise ratio, which is basically the strength of the signal, it would increase your chances of detecting it. But of course, there's that catch that you should be good enough at being able to identify the signal. So if you're not, then even if you have really high SNR, it doesn't really change anything. So while it does make our job easier to recover the signal in the variable TS case because the strength is higher, but at the same time, like I showed, like the other covariance kernels were not able to do it, although they have been used in previous LOFAR results. And that's simply because while this SNR is high, they are just not identifying the right thing, so they mess it up. So we can still show that as something as an improvement, purely based on our machine learning based kernel and not just the SNR. Yeah.
Very naive question. When you were explaining about the foreground, foreground for this 20 centimeter, so is it mostly like the continuum part of the radio, or it's like can be some lines degenerate with the 21 centimeter?
I mean, yes, it can be both.
So what are the nearby like 20 centimeter? Then how will you distinguish that this is the 20 centimeter form that particular exit?
So yeah,
or do we have like other lines too? Usually, like when we estimate the redshift, we have other lines, like 2 lines of a line.
Yes.
So we usually do that.
Yeah. So I think the main idea here is essentially that all the redshifts that you identify the output from those, and you subtract all of that. And so what we do is we subtract the foregrounds, and we treat the rest of the signal as basically like foregrounds plus noise. So once you have you identify the redshifts and subtract all the foregrounds, after that you give like the GPR then deals with the remaining part of it as 21 signal and noise, and that's when it starts looking at it. So you need to basically specify your foregrounds accurately so that it knows until what redshift does it need to go.
Right. Thank you for the talk. I wanted to ask about this slide. So this analysis is done on some family of models.
Yes.
Is that a Grizzly simulation?
Yes.
Okay, yeah. So if you also look at 21 centimeter fast simulations.
Yes, we do, but that would lead to that's the catch I've not shown here. I can show it now. So the catch is that 20 fast signals have really low SNR for the 10 nights case. Like they are less than 10⁻², because they are somewhere here. So what it means is that we would not really detect it, and we tested it, and we got something like this. So at lower K values, we are you can say that, like, again, this is something like an upper limits. Like it tells you that the signal is, like, if it was detected, it would be between these ranges. But the worst case scenario is it's definitely lower than this value, but you are missing it out. Like you're not essentially having it in the predicted range.
And then on the original slide,
Yes.
you are having, on the back. So back to Grizzly.
Yeah.
The signal is increasing. Let's say I take the dashed lines, and then 8.3 is probably, I don't know, let's say not close to the midpoint, I'm guessing.
Yeah, you're approaching the midpoint, like when you're going from 10 to 8. The midpoint, I guess, yeah, close enough.
I just wonder if this is a more extreme model, or so it's quite flat, something that we notice with Grizzly. So I wonder if you were to take, let's say, C2 ray, maybe it would have a slightly different feature. It will be lower at lower K, so higher scales. But maybe that actually will not matter for your bias, because it's related to the signal.
Yes. Yeah, like whatever you give as the input signal would, like we are trying to make the bias independent of that, so that you scale it by that, so that you can make comparisons like that.
And just a silly question, in one of the first slides, you had the different number of nights in the signal. So LOFAR, even 1,000 hours, doesn't seem to give a very high.
Yeah, from what I understand, like, again, I don't know too much about LOFAR, but what they suggested was that some kind of
exotic
models would maybe be in that regime. Yeah. So they say that this box represents the level of fluctuations from non-standard models. So it explores that to a certain extent. But yes, it completely misses out from the conventional models.
Okay, thank you.
Also, it's at a different frequency.
Yes.
So higher frequency, you need more observation time to get the same noise level.
At the lower frequency, higher rates.
Oh yes, at high redshift. Sorry. Any more question for Anshuman? Just want to clarify, LOFAR 1,000 hours, it's related to 100 nights, right?
Yes. Like that's 100 nights are around 1,400 hours, but yeah.
It's because in those plots, your recovered signal was close to 10 to the power 200.
Yes.
Here it's 10-ish.
Yeah.
It's more optimistic, it seems.
Yeah, like there's a lot of things involved in this. Like this was just a kind of like an eyeball estimate for just mid-Western for depiction purpose. Yeah.
Like why these two results from two simulations are very different. It's like,
Yeah, so that was kind of like the idea that they wanted to look at the two most extreme cases of reasonable simulations. So reasonable, but still at the opposite ends of those, so that you can, because again, we have not yet detected the 21 signal from reionization. So you don't really know what's it like. So this was kind of like to say that, okay, it's something between this guy here and this guy here. It could be something in between those two.
I guess even with the upper limits, people have excluded very extreme models that you do not see.
they can be an extreme.
Yeah, like you can exclude models which will go like this because you know that's something below this.
Yes. Is there any more questions for Anshuman? Not, we thank Anshuman again. Axel, you'll close the Zoom link.
Yes.